All right. So in the last class, we were talking about the mass matrix and the equations of motion. We had actually derived the complete set in the last class itself, and we saw that the generalized equations of motion for any rigid body, as long as it's a rigid body, can be expressed in this format, where you have the mass matrix times the generalized velocity vector's derivative plus the Coriolis and centripetal matrix times the velocity vector is equal to the external force that is applied on the rigid body. Notice that so far we have really not talked about any of the external excitations. All that external excitations, we are bunching it here. So all of this is external excitations. Okay, all right. We saw what is the form of this mass matrix, and we also derived what is the form of this Coriolis matrix, and we saw that this Coriolis matrix can now be expressed as shown here. When we originally derived it, we understood that we first derived this with respect to the center of gravity, but now this is expressed with respect to the coordinate origin CO. And that is why we had to make some changes. We had to take care of the fact that the inertia should also be expressed in terms of the body fixed frame rather than about the center of gravity. And that took us some mathematical manipulation to get it into this form that we see right now here. Okay. Notice here that velocity vector which we have is composed of a 6x1 vector. So 3 linear velocities and 3 angular velocities, all expressed in body fixed frame. And the external forces are also expressed in the body fixed frame. So if I expand all of these coefficients out and write them down as individual equations, you'll see that these equations will be pretty lengthy and seem quite complicated. But when expressed in a matrix format, it makes our life simpler and also makes it easy to program it or to manipulate it when we are doing simulations. So the matrix form is a addition which has come fairly recently. So much in the 1960s and so, you would have seen much of this information being given in individual equations as you see here in the expanded form. But then that form would not be very comfortable with respect to guidance, navigation, and control. So we are going to adapt and stick to this matrix form for now. And we'll see that there are some interesting properties of this mass matrix in the Coriolis matrix. And I think we already saw a couple of them, that the mass matrix is symmetric, whereas the Coriolis matrix is skew symmetric, which means that it is equal to negative of its transpose. That property will be particularly useful when we are designing control laws, so which we'll talk a little bit down the line. At that time, you should see that these properties and the matrix form really come in handy when we want to design a controller or navigation system or even a guidance law for these vessels. Okay, let me quickly wrap this portion up. We talked slightly about this, that the mass matrix satisfies the property that it is a symmetric matrix, which means that it is equal to its transpose and it is greater than 0. So when I say greater than 0, what I mean is that the matrix is positive definite, which means that if I take any arbitrary real vector x of size n cross 1 and I take that and multiply it with the mass matrix transpose mb cross x, this will be a greater than 0 value for any chosen value of any arbitrarily chosen x. So as long as x is chosen arbitrarily, we should see, and they are not all zeros, then we should see that this product should turn out to be greater than 0. Notice here that this is a scalar quantity because X is a n cross 1 vector. The matrix is n cross n, or in this case 6 cross 6. So we'll simply call this 6 cross 1. And then this is 1 cross 6. So when I multiply everything out, I should be left with a 1 cross 1 scalar value, and that scalar value will be greater than 0. Whenever a matrix satisfies this property, it is called as a positive definite matrix, okay, and that has certain implications, again, which will be very important when we are trying to design our nonlinear controllers, especially LQR. All right. The mass matrix is unique in the sense that there is only one representation for it, the one that we have seen so far. Whereas when it comes to the Coriolis matrix, the representation is not unique. I can express that Coriolis matrix in different forms. So one form might be as shown here, then another form is here. Both these forms still satisfy the skew symmetric nature of the Coriolis matrix, but I have an option to rewrite things in a slightly different way. Then again, I have the third representation. This is the representation which we saw in the derivations, and you'll see that that doesn't have a 0 in the top left corner. But no matter which representation you choose, at the end of the day, all three are giving you the same value when it comes to computation of CRB multiplied by V. This product is the same irrespective of the representation chosen. And you might wonder how these different representations are coming into the picture. So just to see as an example, we'll try to compare a couple of them just to see what is going on. Okay, so let me try to zoom out here so that I can put them on the same page. All right, there we go. Okay, so let's see representation number 2. We have zeros here, right? And then I have something here, 2 terms here, instead of having 1 term here in the representation 3. Here I have only, this is a non-zero value, but here this is 0. This has 2 terms here, whereas this has a single term here. Let's try to just see, for our sake, whether this matrix multiplication is actually giving us the same thing or not. Okay, notice that we want to now compute CRB of V multiplied by V. That's what we want to compute. Okay, so let's try to do that. Okay. All right. Okay. Okay, so if I apply CRB times V for this representation, what will be my top half of this product that I compute? It will be the first term, 0 times the velocity vector plus this, whatever is there here, multiplied by the angular velocity vector. Is everybody following me?
Yes, sir.
Okay. All right. So 0 multiplied by the velocity vector will be 0. But when it comes to this, we will have minus m times v n dB times omega n dB. So let's write that down. We'll have minus m times v n dB times omega n dB. And then the next term will be minus m times this whole thing multiplied by omega n dB. So minus m times omega times omega NBB times S of R and RBG, isn't it? Isn't it RBG? Not RBG, yeah. Times omega NBB. Just to compare, so this is coming from representation number 2. So if I simplify this, this simply becomes m times omega NBB cross VNB plus m times R cross omega NBB crossed omega NBB. Everybody with me so far on this?
Yes, sir.
Okay. Now let's look at what happens in representation number 3, whether we are getting the same thing or not. So the representation number 3 is this one. So here I have minus m times s of omega NBB. So m times s of omega NBB. That gets multiplied by the velocity vector, correct? And then in addition, I have the second term now, minus s omega NBB RBG. And that will be minus m s of omega NBB s of RBG times omega NBB. It's actually easy to see that this term is the same as this term, correct? Yes?
Yes, sir.
These two terms are the same. Now, it is also easy to see that these two terms are actually not different, because this term will yield m times omega NBB cross VNBB, and we saw that the same thing is what I am seeing here as well. So it's the same terms which are coming in, but I can have multiple representations for the CRB. So notice that the CRB matrix is not the same, but when I take the product CRB times the V, I'm getting the same thing. Is that making sense? Yes, sir. So there is possibility to have multiple representations of the CRB matrix, which can give us the same value of the force. So in that sense, the representation is not unique, and we may have different representations. But certain representations might be very useful to us compared to some other representations. And here is where we come to the point that this representation number 3 is particularly useful. Can you see what is the difference between this representation? So let's try to zoom out a little bit. So between representation number 2 and representation number 3, can you see what is the major difference?
The first term is 0.
Yes, first term is 0, that is definitely there. Anything else can you see?
The representation 2 is like uh, we can write it as sum of maybe symmetric and skew symmetric, that kind of thing.
No, both of them are skew symmetric. That property doesn't get lost.
No, I mean the CRB we can write it as the first in representation 2, we can write it as sum of the symmetric parts like 0, that minus ms v and b. Those two will be the same thing. And the other two will be like the symmetric and the skew symmetric, that kind of thing.
You mean to say you can separate out this part and this part differently, and this part and this part separately, in some sense? Yes, that is true, but I was looking for a more
Sir?
what is visually available. Yes.
Sir, in the third representation, there is no V or beta.
Correct. There is no V and B. So this representation
V
has
and B.
a V and B. Whereas there is no representation. So here I don't have no V and B. Okay, which means that this representation is independent. I'm going to erase this so that it's not confusing enough. Yeah. All right. So this representation is independent of the linear velocity v and b, and that is particularly useful because if we have ocean currents occurring in the system, then what is happening that our relative velocity of the vehicle with respect to the ocean currents is what we will consider when we want to consider the hydrodynamic forces, right? In which case, because the ocean currents will make a dent in our linear velocity of the craft, because when we take a relative linear velocity, our CRB matrix will also be varying. Whereas when we choose this second representation, where we are only not having any V and B, in that case, we can actually neatly write down our velocity due to the current and write down the relative velocity of the vehicle with respect to the current as V minus Vc. Now, that is particularly useful because if the ocean currents are assumed to be irrotational, we can show that the MRB times V dot plus CRB times V is actually equivalent to MRB times VR dot plus CRB times VR, where VR now represents the relative velocity of the vehicle with respect to the ocean currents. Okay, and this we are going to see it again when we actually talk about how the ocean currents are modeled and how the ocean current forces will be included into our dynamics. At the time, we will discuss this more. But for now, just keep in mind that this third representation which we saw, because it does not have linear velocity in it anywhere, it allows us to incorporate the ocean currents into the same modeling without having to need to change any of the existing modeling. We can incorporate the currents. So the idea here is that due to the incorporation of the currents, the CRB matrix itself is not changing. All I'm just doing is instead of the V, I'm just considering VR. Is that making sense? Yes, no? Not making sense? Would you like that explained again?
Yes, sir.
Okay. See, the idea is simple. My original equations of motion on the right hand side, this is what we had, right? And that was actually equal to tau RB. Correct?
Yes, sir.
Now, what we want to do is if there are ocean currents in play, then I want to incorporate those ocean currents also into my dynamics. Okay? And we are assuming, we are making a big assumption here that those ocean currents are actually irrotational in nature. Now, given that, what I want to do, I want to replace this velocities by the relative velocity of the craft, which is the velocity of the craft minus the velocity of the current. So this is the current speed, current velocity. Okay, and this is my actual velocity. Why would I want to do that? Because in that case, I am directly getting the relative velocity of my craft with respect to the current. This can be directly used in the computation of lift and drag computations. Right?
Yes, sir.
Now, that is the advantage which I get. But if I directly want to substitute V for VR, I can't do that unless this CRV matrix, which is actually dependent on V, is independent of the linear translational part. Remember that this V, which we have, it's actually a 6x1 vector consisting of U, V, W, P, Q, and R. Correct? Now my velocity due to the current is UC, VC, WC, 0, 0, 0. Okay, so this is V, this is VC. And I want to actually take a difference between them. So when I take a difference between them, what do I get? U minus UC, V minus VC, W minus WC, and P, Q, and R. Is everybody with me so far?
Yes, sir.
Is V minus VC. Now, if my CRB matrix was in such a representation that the linear part of the velocity actually does not appear in the CRB, then whether I choose this vector or I choose this vector, my value of CRB will come out to be the same, isn't it?
Yes, sir.
Right? So if I choose the representation number 3, which does not have the linear components of the velocity in it, I can simply write this equation which I had before equivalently as I have here, especially with respect to these two parts. Is that clear?
Yes, sir.
Okay, that's the primary idea behind it. Is that clear for everyone? Yes. We will revisit this topic when we discuss about the currents. I'm just kind of trying to hint at the idea at this stage. Why would we want to have a CRB matrix such that it is actually independent of the linear velocity? It has certain advantages when we want to model ocean currents. This part we have not yet covered in detail. We'll really cover it in detail when we figure out what is the ocean currents and how we are modeling them into our system dynamics. That will come at a later point when we talk about environmental conditions. So up till then, have a little patience, but just remember that this representation in which the CRB does not depend on the linear velocity has a potential use case when we want to consider these currents. Do you say that is fair enough?
Yes, sir.
Okay, all right. Okay, now, so far we looked at the nonlinear equations of motion. So today we'll try to wrap up this section by also looking at the so-called linearized 6 degree of freedom rigid body equations of motion. Notice that we had the nonlinear equations of motion and that we want to linearize about some operating point. Now, those of you who were in my maneuvering course, we already know that the operating point is usually chosen as this. Okay, where we are only considering that the ship has a linear forward speed and all other degrees of freedom are 0, which means the ship is moving straight line ahead. In this case, if I want to linearize my equations of motion about that operating point, it can be shown easily enough that this CRB matrix, which is dependent on V, will now convert into a so-called constant matrix, which I'll represent as CRB star. And in a matrix sense, I can give that expression for CRB star as MRB times L, where L is this 6 cross 6 matrix. In which case, you will actually see that if I now multiply CRB star times V, I'm getting only linear terms restricted to in my equations of motion. So here you'll see that this is dependent on R, this is dependent on Q, this is dependent on Q and R, this is dependent on Q, and this is dependent on R. Okay, so all of these terms are linear. There is no non-linearity present here. So this is completely linear. Linear in B. Okay. But that comes at a cost. But before I proceed further with it, let me try to actually bring out this CRB matrix and try to take a look. I know, if I remember correctly, we talked about a complete expression of it somewhere. Did we not have the expanded form written out somewhere? Looks like not. Okay, so maybe it will be worthwhile to write down that expanded form somewhere here. Okay, so what we are going to do is write down the expanded form and see how this matrix is coming about. Okay, all right, let me write it out. We'll take representation 2 as the base to write down this. And let's see to write this down. Okay, so the representation 2, if you remember, is this particular representation. I'm going to expand this out into a 6 cross 6 matrix and write down all the terms. Okay, that would be the idea. Let's see. So then I'll have first 3 terms will be zeros. So 0, 0, 0. And maybe I want to give some space here. And that we already saw was this part 0, 3 cross 3. Now we're going to write down this part which is coming below that. So when I expand that out, I should get minus n times yg times q plus zg times r, and this will become m times yg e plus w, and this will be m times zg e minus v. Similarly, this will be m times xg q minus w. This will be minus m zg r plus xg into d. Actually, maybe I can do this better actually. Rather than write this out, why not I Just pull out it from the book and then we see it there. That will be easier. Correct. Okay, this will be much easier. Is my screen visible?
Yes, sir.
So this I am simply borrowing from your textbook. Only thing is that we have probably not written it out in our course notes, but doesn't matter. So you can see that this is actually that CRB times V, right? And this is getting multiplied by the vector U, V, W, E, Q, and R. And the idea is that after multiplication, whichever term is nonlinear, I want to get rid of those terms. Notice that this matrix is written in a little bit of an off format. This is the first column, this is the second column, this is the third column, and this from here onwards is the fourth column, fifth column, and the sixth column. Is everybody with me so far?
Yes, sir.
Okay.
Sir?
Yes.
Is it matrix CRB or CRB times V?
This is only matrix CRB. We are going to now multiply by V just to see which are the terms which are linear or non-linear. So notice that when we are applying a condition that we want to multiply this with U, you will get some terms. So for example, if I take this term, when I multiply that by U, what do I get? Minus MYG times Q times U, correct? Minus MZG times R times U. Is everybody with me so far?
Yes, sir.
Yes, sir.
The next term will be, I'll have plus MYG times P times V plus M times W times V, right? Where I'm taking this value, multiplying it with V. Yes?
Yes, sir.
Okay, then I will be taking this term, multiplying it with W. Then I'll be taking this term, multiplying it with P. This term, multiplying it with Q. This term, multiplying it with R. And that will give me the so-called fourth value of this vector which I get out. Correct?
Yes, sir.
Okay. Now, notice that we are trying to linearize about the point where we have U, capital U, 0, 0, 0, 0, 0. That is the point about which I am trying to linearize, which means I'm kind of expressing my use, the value of U as capital U plus some delta U, my V as some delta V, some W as some delta W, P as some delta P, Q as some delta Q, and R as some delta R. Where I'm assuming that these delta values are small and compared to, so they're not large values, so we are still in the vicinity of the original point about which we are linearizing it, about which we want to linearize the system. Yes?
Yes, sir.
Now, the idea is that once I take U, V, W, and PQR and substitute these delta values into it, I'll I'll multiply this matrix out with UV, W, PQR. And the idea is wherever I see multiplication between two quantities which are small, so say delta U times delta Q, that value I can approximately take it as 0. Is that making sense? What am I doing?
Yes, sir.
I'm multiplying it out, and wherever I find the product of these quantities appear, because each quantity is assumed to be small, the product will be assumed to be much, much smaller. So I'm actually getting rid of all those terms. So if I only consider about the fourth row for now, just to verify what is going on, can you tell me what will be the output in the fourth row? What will we be left with after we do the multiplication? Let's try to see. This last term which is here, this thing when multiplied by r, will there be any term here which will not be linear, which will be saved? They'll all contain products, isn't it? One will be r square, one will be p times r, one will be q times r.
Yes.
So they all will be going to 0, correct? Under the linearization assumption that any two products will be close to 0, can I say that this term will have absolutely no contribution?
Yes, sir.
Okay.
Yes, sir.
What about this term?
0.
Yeah. That also will be 0, right? Because this thing will be multiplied by q, and we know that that term will also become 0. This term anyway is 0, so it's not going to cause much trouble anyway. Now we come back here. This term will be multiplied by w, isn't it?
Yes, sir.
Will that have any contribution left?
No.
No. What about this fellow? This will be multiplied by v.
0, sir.
This also will be 0. Now this fellow, when will be multiplied by u, that is the only one which will give me some contribution. Correct?
Yes, sir.
Yes, sir. Let's try to see what that contribution should be. Okay. What will come out? Minus myg times q plus zg times r multiplied by capital U. That is the only thing which will be left out. Am I right?
Yes, sir.
Okay. So let's try to see that is what comes out here. You see that the fourth term, that is what is left. Minus myg times q minus mzg times r multiplied by u. Is everybody with me so far?
Yes, sir. Yes, sir.
Okay. So similar process we can find out that all the other cases will come out to be as we see here. It's not very difficult to observe that. So in a linearized sense, what is happening is I can write down this force vector which I have got as some CRB times V, right? Where V is that UVR, UVW, PQR. I can write that down. So if I want to find out what will be my CRB star matrix from here, can you tell me what it will be? What do I get? First row, will I get anything? Is everybody with me what I'm trying to do? I want to find out this fellow given that CRB times V is given by this vector here.
Yes, sir.
Okay, so what should my CRB matrix look like?
First row should be 0.
First row should be all zeros, right? And I'll be looking at a 6 cross 6 matrix. First row is all zeros. Second row, what should I have?
The first term should be
The first term should be?
MR.
No. We want to express this as a multiplication with respect to U, V, R, P, sorry, UVW, PQR. So this matrix that I am finding out multiplied by this vector should give me this vector. So my contention would be that it should be m times u here and zeros everywhere. That making sense?
Yes, sir.
Notice that capital U is not a variable. Capital U is a fixed value, which I know. That is like the design speed of the vessel, isn't it? Everybody with me so far?
Yes, sir.
Okay, all right. What should be the next row?
The fifth term should be minus mu.
Which term?
Fifth one.
Fifth one should be minus mu. All others will be zeros. Right? Okay. Then the fourth one.
The term should be minus mygu.
And then
The last term should be minus mzgu.
ZGU. And then this will all be zeros, right? Is everybody following me?
Yes, sir.
Okay. All right. Similarly, the next one, fifth row.
mxgu.
Where?
Fifth.
Fifth term, mxgu. Right? And then last one.
The sixth term will be mxg.
mxg. Now, that this so-called CRB star matrix, so remember that this matrix is actually nothing but CRB star. That matrix is actually can be obtained as if I took the MRB matrix and then multiplied it by this matrix, I'll get this CRB matrix. Okay. It is not very difficult to show this, so I'll leave it as an exercise for you guys to try out. Notice that you will have only a negative one here in the fifth column and one in the sixth column. That is why you will see things are only happening here and here. Okay, it's not very difficult to see that if I take my mass matrix and multiply by this L matrix, I should get my CRB matrix. Everybody with me so far?
Yes, sir.
Yes, no? This is something which you can verify. I encourage you to do it. It's actually not a very difficult multiplication to do. So you might as well try it out and see what is going on. Okay. So the idea here then becomes that this CRB matrix now can be written as MRB times L times this capital speed U. So only difference is I have pulled as a U common out of this entire matrix. That's all I have done here. Okay, I encourage you to try this out. Only thing which you have to interestingly realize now is that is this CRB star matrix still Q symmetric? Is this matrix Q symmetric, the one which we have written down here? No, it's not, right? Originally, the non-linear version was Q symmetric. But when we linearized it, it no longer is skew-symmetric. So we actually have a loss of certain property of that CRB matrix when we do the linearization. Everybody with me so far?
Yes, sir.
Okay, so that skew-symmetric matrix property is lost during linearization, and that property is somewhat useful for us, especially when we want to design nonlinear motion control methods, which we will look at the later parts of this course. It is really useful when we want to design control laws using what are called as Lyapunov methods. So in that sense, this loss of that property, when we linearize it, we are not very happy with it. Okay, so this is why we typically do not want to, we want to use that CRB matrix property in some sense because its quadratic form is 0. Because it's a skew-symmetric matrix, its quadratic form will be 0. That will come more into play when we talk about energy-based designs or energy-based control methods, which will come later down the line. So just remember that when I linearize the system, it no longer exhibits the same property as the skew-symmetric matrix before. The skew-symmetry is actually lost in this particular case. All right. Okay, so that skew-symmetric property is lost during linearization, and it's particularly useful for when we want to look at energy-based methods and Lyapunov functions. The main idea is that if I take V transpose CRV times V, it is equal to 0 when this matrix is a skew-symmetric matrix. And whereas that is not the case when this is not a skew-symmetric matrix, I can't make this claim anymore. And this claim is particularly useful when we want to look at linear quadratic regulator or Lyapunov functions in order to do backstepping control. So at those places, this will be useful. So for which we would like to kind of preserve it and use it to our advantage in nonlinear motion control. So just keep that in mind. With that, we have come to the end of what you call figuring out what are the kinetics, rigid body kinetics. We have covered everything which there is. Now what we will be looking at is we'll look at the so-called maneuvering models in the coming lecture. So where we will be trying to understand that some of the forces, so here we are only looking at the so-called rigid body forces or the inertia forces due to the rigid body. But we know from our experience in the fluid dynamics that when the vessel is actually operating in calm waters, we will have that so-called added mass coming into the picture. Similarly, we will have additional damping coming into the picture. In addition to that, we also know that when we have these vessels operating in the vessel, there will be these hydrodynamic coefficients which will make an effect. So that is what we are going to spend a little bit of time, but not too much in detail, to look at what are the different hydrodynamic maneuvering models which are important when we want to simulate the motions of the vessel in the sea. So right now we can simulate more or less rigid body dynamics, but we have not paid attention to what is happening on the fluid side. What are those so-called external forces coming in from the fluid side? We will be talking more about that, modeling them, understanding how we can model waves, wind, currents, what is the effect on the hydrodynamics. Those parts we will take a look briefly, and then we will be in a position where we'll know the complete dynamics of our vehicle, and then we can embark really well into navigation, control, and guidance methodologies. I hope at least the plan is somewhat making sense. So that is what you can expect in the coming lecture. We will talk more about maneuvering models, a brief overview, which will be a little more quicker than what you might have seen in your undergraduate course on maneuvering and control. Am I making sense?
Yes, sir.
All right, excellent. So let me stop at this location. Are there any questions before I stop recording? No questions? Okay, so then let me stop recording.